Imagine for a second an AI that can detect a brain tumor with world-class, life-saving accuracy. Now imagine that this AI is instantly available to any hospital on Earth, regardless of how much funding they have or what kind of equipment they're using. Sounds a bit like science fiction, right? Well, let's dive right in, because welcome to this explainer. And today, we're actually looking at a massive, genuinely paradigm-shifting breakthrough in the world of medical artificial intelligence that makes this a reality. Today, we are unpacking a newly proposed framework called MOSAIC. If you've ever wondered how the future of global healthcare AI will actually be built behind the scenes, the real nuts and bolts of it, you're absolutely in the right place. We're going to explore how researchers are finally solving some of the most stubborn, frustrating bottlenecks in medical imaging. But first, I want to start by asking you a profound question. It's a question that represents the absolute core challenge of global healthcare AI right now. How exactly do we train a life-saving medical AI across global hospitals without ever sharing a single patient's private data? Just think about that for a second. We all know AI gets smarter by seeing more data, right? To build an AI that can perfectly outline a brain tumor, it needs to see hundreds of thousands of MRI scans from incredibly diverse patients all around the world. But here's the catch. Medical records are strictly confidential. They are protected by heavy privacy regulations like HIPAA. We can't just dump every hospital's raw MRI scans into one giant, centralized server somewhere. I mean, legally and practically, that is completely impossible. So the billion-dollar puzzle is, how do we get the AI the knowledge it desperately needs without ever actually moving the data? To answer that puzzle, we have to look at what I call the medical AI trilemma. These are three massive, compounding barriers that are currently bottlenecking the entire field of medical AI development. First up, as we just touched on, is struct patient privacy. The data absolutely, fundamentally cannot be centralized. Full stop. Second is high annotation costs. Training a traditional, highly accurate AI requires what we call dense, voxel-level annotations. Basically, an expert neuroradiologist has to sit down and painstakingly draw a boundary around every single slice of a tumor in a 3D scan. Think of a voxel like a 3D pixel. That takes hours, it's incredibly expensive, and frankly, radiologists are way too busy actually saving lives to do this on a massive global scale. Now, the alternative is something called weak supervision, which just uses cheap image-level labels. It's basically a simple tag that says tumor present or tumor not present, which you can just scrape from a standard radiology report. But historically, weak supervision is notoriously noisy and imprecise. And then third, we have missing modalities. And honestly, this is a huge one. You see, an MRI isn't just one simple picture. It's a combination of different sequences or modalities, things like T1, T2, T1C, and FLAIR. Each one captures different tissue contrasts. But out in the real world, hospital acquisition protocols are all over the place. Hospital A might only have T1 and T2 scanners running. Hospital B, maybe they only have time for a FLAIR scan. Okay, to understand why this third point, missing modalities, is so completely devastating to AI, let's use a quick federated baking analogy. Normally, researchers use a technique called federated learning to solve that first privacy issue. In federated learning, the data never leaves the hospital. Instead, the AI model itself travels to the hospital, learns from the local patient data right there on site, and then only sends its newly learned knowledge updates back to a central server to be combined with updates from other hospitals. It's kind of like trying to coordinate a world-class cake recipe across global kitchens. Step 1. The central server sends the master recipe to every kitchen. Step 2. Kitchen A goes to bake it, but they're missing sugar. Maybe their MRI machine just didn't run a T1 scan that day. Step 3. Kitchen B is missing flour. They don't have a FLAIR scan. So, step 4, when they send their wildly different baking adjustments back to the head chef, the collective cake fails completely. Standard federated learning assumes every single hospital has the exact same ingredients. When they don't, the whole system just collapses. And this brings us to the really stark contrast between standard federated learning and actual hospital reality. Standard AI universally assumes it's going to get dense supervision and complete modality availability. It expects identical data formats coming from identical scanners, but the messy reality of global healthcare is that missing modalities completely break standard AI multimodal fusion. When an AI expects 4 types of MRI contrast and only gets, say, 2, it doesn't just perform a little bit worse, it actively starts to hallucinate. Clients with incomplete modalities start generating these spurious false positives. The AI sees some high-intensity artifact in the brain, and because it lacks the proper contrasting scan to verify it, it incorrectly flags it as a tumor. The AI's tumor detection isn't just hindered here, it's dangerously compromised. For medical use, it is essentially ruined. So, how do we fix this?
Enter the hero of our story, the MOSIC framework. MOSIC actually stands for Modality-Agnostic Spectral Alignment for Federated Image-Level Weakly Supervised Tumor Segmentation. Quite a mouthful, I know, but let's break down how brilliant this actually is. When you look at the blueprint of this architecture, it might seem super complex, but it elegantly handles all these missing data pieces in two distinct phases. Phase 1 is happening on the client side, and it's all about modality-robust class activation map, or CAM, generation. Remember those cheap, weak image-level labels we talked about? The ones that just say tumor or no tumor? Phase 1 takes those and manages to generate binary tumor pseudomasks from them. Then we move to Phase 2, which is a federated refinement segmentation network. This phase continuously denoises those rough masks over and over until they are highly accurate. It literally shatters the accuracy ceiling that usually limits weak supervision.
Now, the really fascinating part is how MOSAIC actually handles those missing MRI scans. It introduces what they call a client-specific modality alignment module. And guys, this is the absolute genius hack of the whole system. Instead of panicking when a specific scan, like a flare or a T1, is missing, this lightweight module brilliantly bypasses the missing data problem altogether. How? Because it operates on quantity, not identity. It maps each client's available modalities into a shared latent space based solely on how many channels of data a hospital has, not what the specific data actually is. It requires zero prior knowledge of modality identity. You don't need any complex metadata bookkeeping. A hospital just plugs in whatever scans they happen to have that day, 1, 2, or 3 different types, and the module seamlessly fuses them into a common representation format of a fixed size. It's incredibly elegant. But wait, you might be wondering if every hospital is projecting completely different random combinations of scans into the system. How does the global AI keep its understanding aligned without just drifting into total chaos? Well, that is where MOSAIC's secret weapon comes into play, Spectral Prototype Alignment, or SPA. SPA is a highly advanced, privacy-preserving loss function. Usually, federated systems share spatial features, which are essentially layout maps of the brain. The problem is, theoretically, a bad actor could reverse engineer those spatial maps to reconstruct a private patient image. SPA completely eliminates that risk. Instead of sharing spatial features, it shares compact, frequency domain band energies. In plain English, it breaks the image features down into frequencies. It's almost like turning a picture into a sound wave. It looks at the amplitude statistics that capture the texture and intensity of a tumor, and it completely discards the spatial layout. Because it's only sharing these non-invertible frequency statistics, it is mathematically impossible to reverse engineer the original private patient scans. So it locks down patient privacy perfectly, while still allowing the central server to align all the models from different hospitals into one unified global consensus.
And this brings us to exactly why all that complex back-end engineering actually matters. The visual proof is stunning. We're looking at results from the FETS 2022 dataset, alongside the BRATS SSA dataset, which is specifically a sub-Saharan African glioma cohort. Now, the colors are absolutely critical to understand here. Yellow represents true positives, meaning the AI nailed it. It correctly identified the tumor. Red represents false positives. The AI hallucinated a tumor where there wasn't one at all. And blue represents false negatives. The AI completely missed the tumor. If you look at the competing methods trying to process data from a client that strictly only had one single missing modality to work with, it's a mess. They are practically drowning in red false positives. The standard models completely fail. But then look over at the MOSAIC results. Look at that coverage. It produces by far the most yellow true positive coverage, and it drastically minimizes those dangerous red false positives. It successfully recovers highly accurate boundaries even when critical MRI scans are completely missing from the input.
So what does this all add up to? The crucial takeaway is this number right here, 0.84. This is the macro average DICE score that MOSAIC achieved on the highly heterogeneous FETS 2022 dataset. Now, if you're not familiar, in medical imaging, a DICE score basically measures how perfectly the AI's predicted tumor boundary overlaps with an expert human radiologist's ground truth boundary. A perfect overlap is a score of 1.0. Achieving a 0.84 on this dataset isn't just good, it's honestly staggering. Remember, MOSAIC did this using only cheap, weak image-level labels, operating under strict, mathematically perfect privacy constraints, with clients that were missing vast amounts of modality data. Hitting a 0.84 means it is effectively approaching the accuracy of fully supervised AI models. You know, the models that had the luxury of wildly expensive, dense pixel annotations and perfectly complete datasets. Let's look at the hard data across the board to prove just how dominant this framework really is. This data distills the macro average DICE scores across 3 very distinct multi-institutional clinical datasets: FETS 2022, BROTS-MAN, which focuses on meningiomas, and BROTS-SSA. Take a look at FEBNORM Plus. Up until now, that was really the only baseline explicitly designed to handle missing modalities in this context. On FETS 2022, it scores a 0.74. MOSAIC statistically crushes it with a 0.84. That is a massive 14% relative jump in performance. And remember HARMO-FL? That was another method that tried to align frequencies. It completely collapses down to a 0.60 on some datasets when channels are missing exactly because it just couldn't handle that missing modality gap at the input level. Across all 3 datasets, spanning completely different tumor types, vastly different clinical populations globally, and entirely different missing modality configurations, MOSAIC is consistently sitting at the top. It proves that this modality-agnostic spectral alignment isn't just some clever dataset-specific trick. It is a robust, general, scalable principle for the future of global AI. And speaking of scalable, that brings us to what might be one of the most exciting, practical, real-world features of MOSAIC. The researchers found that, and I quote, "Dynamic new client addition enables previously unseen institutions to join an already trained federation within 0.01 to 0.04 DICE without retraining." What does that actually mean? Well, because that ingenious modality alignment module only cares about the number of channels and not their explicit identity, a brand new hospital with an entirely unique, previously unseen combination of MRI scanners can instantly plug their local data into the already trained global federation. Think about the real-world impact here. This means a rural or underfunded clinic in a developing nation, using older, limited MRI equipment, can map their data right into the system without requiring a massive, computationally expensive total system reboot. They instantly benefit from the world-class, life-saving accuracy of the global model. Ultimately, this is exactly what the future of healthcare AI has to look like. It absolutely has to be strictly private. It must be endlessly adaptable to whatever broken or incomplete equipment a local hospital happens to have. And above all, it has to be life-saving in its accuracy. MOSAIC proves once and for all that we don't have to choose between protecting a patient's fundamental privacy and building a world-class tumor-detecting AI. By leveraging brilliant techniques like spectral prototype alignment and modality-agnostic fusion, we can absolutely achieve both. It really makes you wonder, doesn't it? If an AI can learn to perfectly detect a complex tumor from a fragmented, incomplete puzzle of data, what other supposedly unsolvable medical mysteries is AI about to crack next? If you learned something new today, don't forget to like, subscribe, and follow Open Life Science also for more simple and insightful science explainers. See you in the next one.